Okay. So just a minute, sir. So good afternoon to all. I, Dr. Vivek Asati, Associate Professor, Department of Pharmaceutical Chemistry, on behalf of ISF College of Pharmacy, Moga, Punjab, welcome to respected Dr. G.D. Gupta, sir, Director cum Principal, ISF College of Pharmacy, Moga, Dr. R.K. Narang, Vice Principal, our speaker, expert talk by Dr. Mehdi Irani, Associate Professor in Theoretical Chemistry, University of Kurdistan, Iran, all faculty members and dear students. Thanks for respected Sri Praveen Garji, Chairman ISFCP, for giving such platform for conduct such webinars. So today we have a expert talk on assigning protonation states of protein residues for molecular docking and molecular dynamic simulations. So this is our privilege that we have a renowned, knowledgeable speaker, Dr. Mehdi Irani, with us. Dr. Irani studied chemistry at the University of Kurdistan in Sanad, Iran, where he graduated with a BSc degree in chemistry in 2004. He was a meritorious student of his bachelor degree. He completed master degree program at the Sharif University of Technology, Tehran, Iran. In 2006, he applied for the PhD program at Sharif University of Technology. In the same year, he obtained his PhD degree in theoretical chemistry in 2010 through Sharif University of Technology, emphasizing organic and biomolecular reactions, kinetic and mechanism. After obtaining his doctorate, he began working at University of Kurdistan as a lecturer. He currently holds the position of associate professor at University of Kurdistan. He has experience in chemical kinetics, quantum chemistry, physical chemistry, computer for chemistry student, and general chemistry. As a theoretical chemist, he is primarily interested in enzymatic reaction. So I request to Dr. Mehdi Irani kindly deliver expert talk on assigning protonation states of protein residues for molecular docking and molecular dynamic simulations. So, sir, now you can start.
Thank you, Dr. Vivek, for inviting me and introducing me. Okay, let's share my screen and start the lecture.
So, sir, do you want to share your slides? Okay.
I'm sharing. Okay. Is it now? I think that it's shared now. Do you have my screen? Okay, the lecture is about assigning protonation states of protein residues for or before molecular docking and molecular dynamics simulation, which is an important step before performing such simulations. But first, I want to introduce proteins. Talk some about proteins. I want to talk about primary structures of protein. As you see here, proteins are formed by reacting amino acids. Amino acids have a shape like this. Let me start from here. They have a carbon atom. Yes, they have a carbon atom which is connected to an NH2 group, and the carbon atom is connected to a carboxyl group like this. And this carbon is also connected to one hydrogen.
Sir, you are not audible.
Yes. Sorry. Do you have my screen? Is there any problem? Okay, I think that we can continue. And this carbon atom is also connected to the group, I call it R group, and another amino acid is here. I write it
Okay,
by
sir.
blue.
Audible, sir.
Okay. This carbon atom, H hydrogen atom, the carboxyl group, and the NH2 group. This nitrogen atom here can attack here, can make a nucleophilic attack here, and without a water molecule, then a connection between these two amino acids can be formed here, something like this, H2N, C, H, or let me call this one as the side chain of this one as R prime. Okay, and CO. Okay, and the second amino acid is CHR prime and CO, and this bond can be connected to the to another amino acid from another group. This forms the primary structure of a protein, as you see here, which is composed of connecting some amino acids to each other. After forming the primary structure, the secondary structure can be formed, which the secondary structure of protein arises from the hydrogen bonds from between atoms of polypeptide backbone, as you see here. I forgot to introduce that we have backbone here for a protein in the primary structure, and some groups, which I call them R prime and R double prime and so on, are dangling from it. The backbone atoms can form hydrogen bonds to form the secondary structures. Alpha helixes and beta sheets are two types of secondary structures, as you see here, which are formed by hydrogen bonds between the backbone atoms of a polypeptide chain. An alpha helix, as I summarized here, is a right-handed coil with 3.6 residues per turn, as you see here. For example, if this is one turn, in one turn we have about 3.6 amino acids, which are formed between carbon, oxygen, and one amino acid, and amino nitrogen of another amino acid 4 residues away. And also we have beta sheets, which we can see in this slide better. Beta sheets is a flat or pleated structure with hydrogen bonds between adjacent strands of polypeptide chain. The strands can be parallel. As you see here, we have 2 strands of amino acids here, which are formed by making hydrogen bonds between groups, and primarily the backbone groups of adjacent amino acids, as you see here. But as we see here, hydrogen atoms are so important here to forming secondary structure of a protein, and also they are important in forming the final structure of a protein, which is something like this. We call it ternary structure. But what is important is that these hydrogen atoms that you see here are missed from PDB structures. A user have to assign the protonation states of amino acids before performing molecular dynamics and or molecular docking simulations. As you see here in this slide, the amino acids are separated in some categories. The first one are amino acids with electrically charged side chains. As you see here, we have arginine, which has a positively charged side chain here. It's positively charged. Histidine, which can either be neutral or positively charged. I will talk about it more. And lysine, which has a positively charged side chain, and ASP, aspartic acid, and glutamic acid, which they have negatively charged side chain. The other amino acids are with polar uncharged side chains, as you see here: serine, threonine, asparagine, glutamine. They have polar but uncharged side chains. The other group are special cases like cysteine, selenocysteine, glycine, proline. And the last group are amino acids with hydrophobic side chains like alanine, valine, ILE, leucine, methionine, phenylalanine, tyrosine, and tryptophan. Molecular dynamics programs or modules of molecular dynamics programs like TLIP of Amber, can add hydrogens to the amino acids. But what is important that how many hydrogens they should have to add to histidine residue, to a ASP residue, and to a GLE residue, and sometimes to cysteine residue, arginine, and lysine residues. Okay, I'm going to talk about these possibilities. As you see here, the main philosophy of assigning proper protonation states of titrable residues is that charged groups can only be presented on the surface of protein. What are the charged groups? Charged groups are arginine, lysine, GLU, and ASP, and the protonated, completely protonated histidine residue, and so on. And there should be no buried charge, not involved in ionic pairs. Sometimes these groups form ionic pairs inside the protein. Let me draw an imaginary structure, protein structure here. Then these groups can be present on the surface if they are charged. It doesn't matter. For example, we can have GLU, which is negatively charged on the surface. We can have ASP minus here. We can have ARG positive here and LYS positive here. But what happens if these groups goes inside the protein? Okay, for example, if we have a GLU residue inside the protein, when this GLU residue is buried inside the protein, in only one condition it can be charged, or it can be negatively charged. The condition is that there should be a positively charged ion pair for it. For example, an arginine, positively charged arginine group, if present inside the protein, then this group can be negatively charged. Or sometimes it can be coordinated to a metal ion, for example, to a Zn ion. Then at this case, it also can be charged. Or sometimes the GLU residue are a part of active side. Then this time it can also be negatively charged. Otherwise, we have to neutralize the GLU or ASP groups, giving it one extra proton. I will talk about how giving an extra proton to these residues in the following. Okay, let me show you an example from my web page. I paste the link of this page into the chat box, then you can work on it later. Okay, let's go back to the web page. I explained everything here, how we can assign proper protonation states of amino acid residues. I start from here. Point 7, assigning protonation states of titrable residues. Some amino acid residues can have more than one protonation states, as you see here. As I said, they are arginine, lysine, histidine, GLU, ASP, and cysteine residues. Protonation states of these residues are not identified in the PDB files, since there are no hydrogen atoms in such files. For first subunit, okay, here is the procedure. Let me show a PDB structure here. For example, I want to download the 1QH5 PDB structure. Sorry. Okay, it's the structure of human glyoxylase 2. I download it here as a PDB format. Okay, then I open it on a PDB visualizer. You can open it with any PDB visualizer. I use RASMOL to visualize it. Okay, as you see here, the protein is composed of of 4 chains, as I remember. 2 chains are in the left-hand side and 2 chains are in the right-hand side. Let me show them display them in balls and the stick option, and display ball and stick, space filled ball, display ball and stick. As you see here, we don't have any hydrogen atoms here, and we have to decide which group is charged and which group is neutral. Okay. I want to show you the GLU groups here. I can select GLU, executing select GLU. Then I display them with display spacefill. Okay, you see here all GLU groups. As you see, most of the GLU groups are on the surface of the protein. Then we can leave them charged and do no action. But some GLU groups, as I see this one here, which is GLU 218, is buried inside the protein. Let me select GLU 218 or another. Okay, I open it again and select 218, display spacefill. Okay, as you see here, it is buried inside the protein. Then we have to look at its neighbors to see if there is any ion pair with it or not. For this reason, I execute the command restrict within, for example, 3.5 angstrom from this residue, which is its number is 218. Then I display those group display balanistic here. Okay, let's see what is this nitrogen atom here. It is ASN, the nitrogen of ASN, and this one is alanine, backbone of alanine. What is this one? This is the phenylalanine group, and this group is tyrosine. Then, as I say, this group is buried inside the protein with no ion pair. I have to neutralize it by changing its residue symbol to GLH. Then I have to change its symbol in the PDB file from GLU to GLH. Okay, and let me show another example of for example, arginine groups. I can select all arginine groups by this command. Display them in spacefill format. As you see, most of the arginine groups are on the surface of the protein. As I see, all of them are on the surface on the protein. Then we don't need to change anything here for any arginine group. Let's look at the two ASP groups. I select ASP groups. ASP, for example, I execute select ASP here, display spacefill. Okay. As you see here, all the ASP groups are on the surface. Then they can be charged. However, this one is a little suspicious. Let's look at its number. It's ASP 134. Let me show it alone inside the protein. I select 134, and I show it. I display it with the spacefill. Okay, as you see, it is buried inside the protein. Then I have to find if there is any ion pair with it or not. For this reason, I execute this command, restrict within 3.5 from 134. Then I display them with balanistic format. Okay. As I see here, this is a Zn group, Zn atom. This one is a Zn atom. Actually, they are Zn ions. And this ASP residue is coordinated to these Zn groups. Then we don't need to change its protonation state. It's buried inside the protein, but since it is coordinated to metal ions, it can be left as a charged group inside protein. Okay, let's get back here into my web page and find out about some other groups. Okay, I talked here about the protonation states of arginine and lysine groups, how we have to assign them, and also protonation states of GLU and ASP residues. I talked some about them. Let's talk some about the protonation states of histidine residues inside this protein. Let me zoom on this. Okay, we see here the structure of a histidine residue. It can be protonated on this nitrogen atom. This nitrogen atom's name is E. We call it Ne2. And the name of this nitrogen here, it's ND1. It's in the delta position with respect to the alpha carbon. This histidine residue can either be protonated on Ne2 atom, it can be protonated on ND1 atom, or it can be protonated on both ND1 and Ne2 atoms. At that case, it is positively charged. Let me show it in another slide here. The histidine residue is like this. We have a nitrogen atom here and the nitrogen atom here. This one's name is Ne2 and this one's name is ND1. The first possible protonation state of this group is that it is protonated from ND1 atom. At this case, the net charge is 0. The second possibility is that it is protonated on Ne2 like this. At this case, also the net charge is 0. And another possible protonation state of this residue is is that it is protonated on the two nitrogen atoms here. At this case, the net charge is +1. It is positively charged. For this case, for the first case, I call it, or we name it as HID. For this case, when it is protonated on Ne2, we call it HIE. And at this case, we call it HIP. The default residue name inside the PDB file is HIS. Then if we decided that it is protonated on ND1, we have to change the residue name to HID. If we decide that the protonation is on Ne2, we have to change its residue name to HIE. And if it is doubly protonated, we have to change its residue name to HIP. Let's check some of the histidine residues here in this protein. I select all the histidine residues here. Let's select HIS. Display spacefill, for example. As you see here, we have too many histidine residues inside the protein. Then those histidine residues that are buried inside protein most probably are neutral. They are HID or HIP. Let's, for example, check this one. Histidine 420. I select histidine 420. Select. No atoms is selected. Let me. No, I have to select 54, HIS 54. Then I display it with the space fill as a space fill. As you see here, it is buried inside protein. Let's look at its hydrogen bond pattern inside the protein. For this reason, I can execute this command: select or restrict within 4.0 and from 54. Okay, then show them with balls and the sticks. Okay, as you see here, this histidine residue is coordinated. As you see here, it is coordinated to a Z ion inside the protein. Then since it is coordinated, then this nitrogen atom, which is Ne2, cannot be protonated. Then its protonation state is HID. I write it here that histidine HIS 54, the protonation state is HID. Let's look at another histidine group inside the protein. I reopen the file and reselect the histidine groups. Display space fill. Okay, this histidine group is histidine 54. We checked it. Another histidine group is this one, which is histidine 173. Okay, let's check it. I select 173 and show it as display as space fill. We have two histidine 173. Okay, then let's visualize it. Visualize the hydrogen bond pattern of it inside the protein by this command: restrict within 4.0 from 4.0 angstrom from 173. Okay, then I display it like this. As you see here, this histidine residue is coordinated also to these Z ion, as you see here. This is the Z ion from its Ne2 atom. Then it cannot be protonated from Ne2. Then we have to change its protonation state to HID. Then I also change the protonation state of HIS 173 to HID. Okay, let's check some cysteine residues inside this protein. Let me see if there is any cysteine residues. I can select them, select them by executing this command: select CYS, display space fill. Okay, I have 1, 2, 3, 4, 5 cysteine residues per group or per chain in this protein. I want to check this cysteine residue here. Its number is 171. I select CYS 171 space fill. Okay, it's buried inside protein. It is most probably neutral. Then I look at its hydrogen bond pattern by this command and display them with the balanistic format. Okay, as you see, there is no metal ion that the cysteine is coordinated to it. There is no cysteine group to make a bridge between the sulfur atoms. Then we have to leave it as CYS or leave it protonated. This was a summary of assigning protonation state of protein residues as a summary from this page, which I pasted its link into the chat box. You can try it and make download your PDF file and follow this structure and ask me any question. If you have my contact information is here, you can find it from my homepage here.
Okay, sir.
Okay, thank you.
Okay, thank you, sir. So, sir, what impact of this protonation in molecular docking process? So, when we go through any software, we can see there are a protein preparation wizard. So, we just prepare the protein. So, all these missing hydrogen can be corrected through that protein preparation wizard?
It would be better if you assign the protonation state before doing molecular docking and molecular dynamic simulations. For example, this residue CO, which is a carboxylic or GLU residue, by default in molecular docking, it is negatively charged. And we know that the charges or partial charges are very important in molecular docking. But then at this time, it attracts the positively charged parts of the ligand in molecular docking to this group. But if we decide that the protonation state of this group be like this, OH, then at this case it is neutral. Then in molecular docking we have no such net negative charge here. Then this positively charged part of the ligand of the substrate will go somewhere else on the protein, will not go toward this residue. Then we can conclude that it is very important in molecular docking assignment.
So, sir, yes, correct, sir. But, sir, when we prepare protein, that we do not check such type of thing that what the charge present. So, how can we identify that a negative charge is still present on any amino acid? So, we have to check through different software.
Let me show you. Let me download that PDF file here. Well, I think it was 1QH5. Okay. For example, if I want to change the protonation state of one of the GLU residues, I have to find its residue name inside the PDB file. Here, as you see, the residue name of GLU4 is GLU. Okay, I want to protonate it on one of its OE atoms, for example. At this case, I have to change its residue name from GLU to GLH. I have to change all of these to GLH. And the TLIP modular amber identifies that it is neutral and adds one proton by default to its OE2 atom. And if I want to change the protonation state of ASP on ASP group, by default, ASP group is negatively charged if I leave it as its residue name as ASP. I want to neutralize it, then I need to change its residue name from ASP, from ASP to ASH, and so. I summarized everything in the web page.
Yes, sir. Yes, sir. I understand that the NAM is very important. I've seen so many NAM change. Previously, I do not understand that the NAM due to this protonation. But today I understand that is due to the protonation. So actually we perform such docking and synthetic study. Actually basic background is related to synthesis. But we perform such virtual screening, pharmacophore development, 3D QSAR and docking. So sir, that really very, very nice presentation, and we get a lot of knowledge to this presentation about the protonation of different amino acids. So sir, thank you for being with us and giving this presentation. Thank you, sir.
Thank you for inviting me and hosting me. See you sometime.
Okay, sir.